Let's do it. Review. All right, so number one, define the following terms. We have an indicator, which hopefully you guys already know is something that will give you a physical change when the solution changes, so that you can see it. It's observable. The acid's a proton donator. The base is a proton acceptor. Something that's amphoteric is something that can act as an acid or a base. And what common substance did we say was amphoteric?
H2O.
Good. Water. Very good. Thank you. If something is polyprotic, what do we got going on there?
More than one hydrogen.
Good. It can give away more than one proton. Very good. And so there's diprotic, like H2SO4. There's triprotic, like H3PO4. And then an acid-base titration is where we actually use something of known concentration, whether an acid or a base, to determine the concentration of an unknown acid or base. And you're doing a neutralization reaction, correct? Remember, when you neutralize something, you have enough acid and enough base to actually turn everything into salt and water. There's none left, basically, that we're thinking of. Okay. Number two, what are the three characteristics of an acid that you learned in this chapter? We already went over those. Sour, electrolytes, they're covalent electrolytes, and turn blue litmus paper red. Whereas on number three, for the bases, they are bitter, slippery when mixed with water, and turn red litmus paper blue. We actually saw that. Number four, the two acid-base indicators you learned in this chapter would be litmus paper, and what's the other one? Cabbage juice, which I think he's looking for anthocyanins because it is chemistry, but you're absolutely right, it's cabbage juice. But the indicator within the cabbage is anthocyanin, okay? For your test, what you need to remember about the anthocyanin is that when it is in an acid solution, it will appear pink. When it becomes neutral, that solution becomes neutral, it will turn purple. And then when it turns into a weak base, that solution turns into a weak base, the anthocyanin will turn blue. And when it's in a strong base, the anthocyanin turns a greenish yellow. And so this is what makes it such a good indicator, is because it actually can tell you whether it's an acid, if the solution is neutral, if it's a weak base or a strong base, by something very obvious, which is in the color. And you do need to know this to answer some questions on your test. So even though it wasn't made very specific in number four, I want to make sure you know this so that you can answer those questions. Let's see. Is lye an acid, base, or neither? It's a base, and its common name is sodium hydroxide. And you're going to be using that today, and we'll get back to that, but I want you to use it very, very carefully, because it can be dangerous when it's concentrated, and you're making your own concentrate today. And I know you feel hot. It burns your hand. Andrew mixed it for us the last time we used it. Did you really?
Yeah.
I am so sorry.
Sorry.
All right, so take that into account. And was it from touching the outside of the container? Okay. The heat from the outside of the container actually blistered his fingers. So he didn't get it on his hands. So what you're hearing there is when you mix it, expect it to be hot enough that you do not touch the glass near where the solution is. Do you understand? I'm so sorry, Andrew. Even if you wear gloves, all we have is rubber gloves. That's not going to protect you from the heat. Trust me on this, it's not. So I want you to be very, very careful, okay? Okay, let's see. Well, but you know what? In the other book, we just use ammonia. In this book, you're really doing more chemistry, so you're gonna have to be careful, okay? Otherwise, you'll end up like Mrs. Frady's, destroying clothes, jumping under showers, and moving people quickly. You know, you don't want to do that. Okay, let's see. Number 6, fill in the blank with either acid or base. Blank are found in many of the things we eat and drink. What do you think? Acids. And blank are in household cleaners. Bases. Very good. Identify the acid or base in the following chemical reaction. For A, what is the water, the acid or the base? For A.
Acid.
We are on number 7, and I'm asking you for A, which is water, an acid or a base?
Acid.
It's an acid, because you see on the right-hand side, it has lost the proton and turned into the hydroxide ion. B, now what is the water on this one?
Base.
It's the base because here it's received the proton, and on the right-hand side, on the product side, it's H3O, the hydronium ion. Am I saying that right? Hydronium, that's the one, right? Yeah, thought so. Okay. Had trouble with that last week. And then C, HCN, is that the acid or the base?
Acid.
Yeah, that's the acid because on the right-hand side, it's lost its proton. Very good. It says, give an example of an amphiprotic chemical. Water. Okay. And it says, identify the following as acids or bases. What about ammonia? That's an H3. That's a base. What about HNO3? Acid. What about HC3H5O2? Acid. What about lithium hydroxide? Base. What about zinc hydroxide? Base. Good. Okay, number 10. Suppose you were told by a chemist that citric acid is an acid that can donate 3 protons. How would you rewrite the chemical formula to make citric acid more recognizable as a polyprotic acid? H3, very good. So you go H3, C6, H5O7. There you go. You just take those 3 protons out of the H, put it up front, and then rewrite it. Very good. Number 11. HBr is a strong enough acid that it will make water act as a base. Remember, that's what makes an amphiprotic substance act as one or the other when it's with a stronger version of one or the other. And so let's see. What is the chemical reaction between HBr and H2O? Be a metal, and you'll know it's ionic, okay? Remember the metals are on the left side of the chart? Okay? So that's covalent. What does it make, an acid with a covalent base? Ions. This is going to turn into the hydronium ion. So it's going to leave this guy like this, isn't it? That's it. And it's balanced. Okay. Let's see. Determine the reaction that occurs between the following chemicals. So, first one, we have sulfuric acid plus ammonia. What's the first question I ask myself? Good. Is it ionic or a covalent base? What about that one? Does it have a metal up front? No. So is it ionic or covalent? It's covalent. What am I going to make? Everybody, what am I going to make? Thank you. So this is going to turn into what? What ion does this turn into? Very good. NH4 plus 1, ammonium, right? It's one of the ones we have memorized. And how many of these protons is this going to give away? 2. So I'm going to need 2 of these to receive, and it's going to produce 2 of those, correct? And so what's going to be left is the sulfate ion, which you have memorized, so you should be able to come up with that. Correct? And it's balanced. If you do it that way, it should be balanced. All right, let's do the next one. Aluminum hydroxide. Okay. Now, is it ionic or covalent? That's ionic because it's got a metal up front. So what am I going to make? Salt and water. How many waters am I going to make? 3. So I'm going to need 3 of these hydrogens to go with 3 of those hydroxides, aren't I? Right? I'm going to make 3 waters. That's going to leave aluminum, fluoride. Watch your charges because that helps you. Flip-flop. And if you did your charges correctly and your water correctly, it should be balanced. Got 3 of those, 3 of those, 1 of those, 1 of those. Yep, it's balanced. Right? Okay, let's do the next one.
Why do you write HOH instead of H2O?
Very good question. Then I can see that 3 of these are getting together with 3 of these.
Okay.
It's literally to help me see what's happening. That's exactly why. That's a good question, though, because I could write it as H2O. But I want you guys to see what's happening. Let's see. We have phosphoric acid. Calcium hydroxide. Okay. Ionic or covalent?
Ionic.
Ionic. Calcium is on the left side of the chart. It's ionic. You guys need to look, okay? So what's it going to make? Salt and water. How many waters? I've got 2 here and I've got 3 here. So how many waters?
6.
Come on, guys, think fractions. You can't just add these two. You have to come up with the lowest common multiple, right? What's the lowest common multiple between 2 and 3? 6. Okay, so I want to make 6 waters. So I know I'm going to have to multiply this by 3 and this by 2, aren't I? Okay? That gives me my 6 waters. Now, and if you don't want to do it that way, you don't have to. You can just do water. You make your ion, then go back and balance the whole thing, and that's fine. This is easier in my opinion, but if it's not for you, do it the other way. Okay? Then we have calcium, which is +2. And then we have phosphate, which is -3. So we get our 3 here and our 2 here. Whoops. There we go. Then we count. We have 3 calciums, 2 phosphates, 2 phosphates. We have 6 hydroxides. Andrew, this is why I did it this way. 3 times 2 of these, I have 6 hydroxides. I can see it. And I have 6 hydrogens. Does that make sense? That's exactly why I write it that way, so I can see it. Okay? Alrighty. Last one. H2CrO4. Okay, is it ionic or covalent? Good, that's ionic. So what am I going to make? Salt water. How many waters am I going to make? 2. There's 2 of these, 2 of these. So I'm going to go 2 waters. I'm left with that and that. Now, I can look at this, even if you don't have this memorized, I can look at this and tell it's a -2 because there's 2 hydrogens with it. So it's got to be a -2, doesn't it? Okay? All right, so this is a 1-to-1 relationship, so I just disappear it. And it's balanced. Yes, sir.
I got it.
Are you okay?
I got it.
Okay, good. That's good. I want you to get it. Number 13. This one, we could come back, but number 13, it says, you see 5 clear solutions labeled with the following pHs, and then it gives those pHs. One of them is a solution of sodium chloride and water. Regular old salt and water. What's its pH going to be? 7. I like how he did this. This is, you have to think through these, don't you? B, one of them is a very concentrated solution of strong acid. Which one is it? 0.1, very good. C, one of them is a sour but pleasant drink. Which one? 4.5. D, one of them is glass cleaner that you buy at the grocery store. Which one is it? 9.0. One of them is a very caustic base. Which one is it? Good, very good. Good job. Okay, 14. What volume of a 3.17 molar solution of sulfuric acid would be required to neutralize 750 mils of a 2.12 molar solution of sodium hydroxide? Now, once again, hopefully everybody here is past hyperventilating when you see these kind of problems, right? You guys doing all right? No, not yet? You're not past hyperventilating when you see these problems yet? Okay, you want to breathe.
When you see these problems.
I'm sorry?
It's healthy to hyperventilate when you see these
Is it? Okay, then you're allowed to hyperventilate, but just don't pass out. When you see these problems, I want you to breathe, I want you to pray, and I want you to think, Mrs. Frady's told me I can do this. And I know you can do this, but you need to have practiced, and you need to work through the process. The process is to first do the reaction, then balance the equation, then put the given and the get to into the equation, then worry about figuring it out. Because once you do that, if you will write out the balanced chemical equation and put the given where it's supposed to be and the question mark where it's supposed to be, all of you know it goes through the moles. All of you know that. And you know how to get from one place to the moles and then to the other place. So you really can do this, can't you? Yes, you really can. But you have to work through the process. So this first one, we are told we're working with H2SO4 plus sodium hydroxide. Okay. Is it a salt or, excuse me, it's an ionic base, so it's going to make a salt and water. I'm sorry, I already messed up and said it. Okay. So how many waters is it going to make? 2, because I have 2 of these. So I'm going to need 2 of these, don't I? So I have 2 of those. So I have 2 waters. And then I have sodium. And I have sulfate. So that, excuse me, this is a +1. I know what sodium is really. It's a +1. So this is going to flip-flop. There you go. And if there's any doubt, go on your periodic chart. It's in group 1. It's a group 1 metal. That's why it's a +1. Okay. Yes, sir.
For the purpose of these problems, would it just be easier to like just do the water part? Because then you're balanced, because you know how many waters it's going to be?
Yeah, considering you're only using that part of the equation, you could, but I'm the teacher. I'm not allowed to get away with that. Okay. But yes, you absolutely could. All right. So now let's look at the given information. We are told that the H2SO4 is 3.17 molar. And to neutralize, and we've got a 2.12 molar. And we are given 750 mils, which I know this is in moles per liter. So I'm going to make the 750 mils into liters. Significant figures. There we go. I just moved my decimal place back 3. Okay. And then the question is, what volume of this? So now I've written my balanced equation. You guys can all do that. Write your balanced chemical equation. Put your given in and your get to. Once you do that, you know to get from here to here, and you know you're going from here to here because that's where the question mark is. That's where the numbers are, without a question mark. So to do that, you're going to go through moles. You know that. So we got to get to moles, and we know that molarity is actually moles per liter. And right here we have the liters. I can write, really. And so that is going to give us 3 significant figures, 1.59. Liters cancel. I'll be left with moles. And that's moles of sodium hydroxide. So far, so good. Then I want to get from here to here. So that's times line, moles of sodium hydroxide to moles of sulfuric acid. 1, 2. So it's going to be half of that. And so that's going to be 0.795 moles of sulfuric. Okay? Now I'm here, and that's where I wanted to get to. 0.795 moles of sulfuric. I can write. And I'm trying to get to the liters. Now, I know that molarity, I'm just going to show you his way first, is this divided by liters, so I just solve for that, don't I? Okay? And that's absolutely true, but me being the weirdo that I am, I told you to just go ahead and take the molarity and flip it, because that's really what you're doing. Right? It's really what you're doing. And then the moles will disappear, and you'll be left with the liters up top. And the liters in this case is going to be 0.251 liters. But what's the most important part of this whole thing? The setup. Because you can all do it once you get the setup, right? Is anybody getting stuck when you get here? You guys are okay there? Even if you have to just go moles per liter equals, and then you put the molarity in, and then you just solve for the liters on the bottom. You can do that. Because you just root, and which is really what that is, and you know. Okay? Number 15. A student needs to neutralize 1.5 liters of a 5.6 molar hydrochloric solution. how many grams of aluminum hydroxide should be used. Okay, so here we are going to first, remember, when you do these, you're going to write out the reaction, you're going to balance the equation, then you're going to add your given and your get to, and then we'll go from there. So first, let's write out the equation, and we know that we are reacting hydrochloric acid with aluminum hydroxide, and he was kind enough to actually give us those so we don't have to figure them out. Now remember, we're going to make waters, and here we can make 3 waters. So I'm going to make 3 waters, and then what's left is aluminum, which is a +3. I'm going to write it the way he does it. And then the chloride ion, which is a -1, so we're going to flip-flop. So this gets the 1, this gets the 3. Then we're going to make sure we're balanced. We have one, we got to put 3 of these, don't we? Shame on me. There we go. Okay, so now we have the 3 chlorines. We have the 3 hydrogens, which are, remember, this is actually this, isn't it? And we have 3 of those, just so you can see it. So we have 3 hydrogens, 3 hydroxide, 1 aluminum, and 3 chlorines. So we know that we're balanced. Okay, so now we're balanced. I'm going to put in the information, and we're told we want to neutralize 1.5 liters. So I'm going to put 1.5 liters, and then that is a 5.6 molar solution. And remember, molarity is moles per liter. And now we want to know how many grams of aluminum hydroxide it would require to neutralize that. So we're going to start with where our moles are, because we need to go from the moles of this to the moles of this. So this is moles per liter. The molarity is 5.6 moles per liter times, and we have the number of liters given to us, so we put that like this, and that way it'll cancel, and that will give us the number of moles, which is in 2 significant figures, 8.4 moles of HCl. And that gave it to there. Now we go across the mole bridge, so I'm going to get rid of that. We're going to go times line, and we go moles of HCl, and we're trying to get to the moles of aluminum hydroxide. There we go. That's it, aluminum. Okay, this gets a 1. This gets a 3. And so that's going to give us, in 2 significant figures, 2.8 moles of aluminum hydroxide. I'm going to come back over here. So we have 2.8 moles of aluminum hydroxide. And we need to get to the grams of that, so we're going to go moles of aluminum hydroxide on the bottom, so those will cancel. Grams of aluminum hydroxide on the top. There we go, which is legal. One of these, if you add it up, its gram molecular weight is 78.01. So in 2 significant figures, that's going to give you 220 grams of aluminum hydroxide. And that number is in 2 significant figures. Now, what came out of your calculator, that's why I wanted to look, what came out of your calculator was 218.428. But you have 2 significant figures over here. You have to represent this in 2 significant figures. So you could have written it as 220 that way, because that's 2 significant figures. That 0 is not to the right of the decimal at the end of the number. Or you could have written it as 2.2 times 10 to the second grams of aluminum hydroxide. But it had to be this way. It couldn't be this way. Make sure for your test that you do that correctly. Number 16. What is wrong with the following statement? The end point of a titration occurs when the number of moles of acid and equals the number of moles of base. And so what's wrong with that is it's not when the 2 are equal, it's when there's enough to neutralize each other. So it's not a matter of them being equal, it's a matter of them neutralizing one another. I just want you guys to know that I'm very proud of you, because this is real, solid chemistry now. Do you realize how many different things you have applied here to do this? You've learned how to do the chemical reaction. You have learned how to balance the equation. You have learned how to use the molarity, which is the concentration of a solution, to get from one place to another in a chemical equation. I'm very proud of you. You're doing a really good job. I just want you to know that. 17. Bromothymol blue is an indicator that is yellow with a pH of 0 to 6.8, is green at 6.9 to 8.2, it's blue at 8.3 to 14. You are told to use it as an indicator in acid-base titration. The titration starts with an acid in the flask. What is the initial color of the flask if it's an acid? Yellow. What will it change to when you reach the endpoint? Green. Good. 18. 15.0 mils of a solution of H2CrO4 of unknown concentration is titrated with 1.16 molar solution of potassium hydroxide. If it takes 13.1 mils of potassium hydroxide to reach the endpoint, what is the concentration of the H2CrO4? So let's do that one. First, we are going to write up our reaction. And so we have our acid, and then we are reacting it with our base, potassium hydroxide. This is an ionic base, just like the last one we did with the aluminum hydroxide was an ionic base. So we're going to make salt and water. And so we're going to make 2 waters. So we're going to need 2 of these, aren't we? And so we go 2 waters, and that'll get that out of the way. We've got that and that now. So now we're going to go plus, we have potassium, and then we have chromate. And the chromate is a -2. And in case you don't remember that, you can see that it is because there's 2 of these attached to it. So that means this is going to get the 2, this is going to get the 1, so we can get rid of these charges. Check your balancing. There's 2 of these, there's 2 of these, there's 2 of these, and there's 1 of these. Okay, so we're good on our balancing of our equation. Now we go ahead and add the given and get to information. We have 15 mils of this. And so we are going to, I'm going to go ahead and make that into liters. So I'm going to move the decimal place back by 3, and it's in 3 significant figures. Okay, so it would be 0.0150 liters. We titrated with a 1.16 molar solution of potassium hydroxide. It takes, once again, I'm going to put this in liters. It's 13.1 mils, so I'm going to move the decimal place back by 3, so it's going to give me 13.0131. That way I've moved it back the 3 places, liters. That's how much it took to reach the end point. And so we are looking for, what is the concentration? We are looking for the molarity of the original acid. So we have to start where there's no question mark, drive to where there is a question mark. We're going to have to go through the moles to get there. So we want to get to moles, and we have moles right here because this is actually moles per liter, isn't it? So we're going to use that, 1.16 moles of potassium hydroxide per liter. That's what the molarity represents, times line. We need to get the liters in here, so I'm going to go 0.0131. That's my 13.1 mils, and that will make the liters leave, and that will tell me how many moles of this particular substance, the potassium hydroxide, we have. We have 3 significant figures, so we're going to go 0.0152 moles of potassium hydroxide. Okay, now that we're there, we can go through the mole bridge to get from here to here. So we're going to go times line. We put whatever's here on the bottom, and whatever we're trying to get to on the top. Okay, this one gets a 1. Potassium hydroxide gets a 2. So this is going to give us in three significant figures, this is going to give us 0.00760 moles, and that leaves us with the H2CrO4, the acid that we started with. Now that we have the moles, we can figure out the molarity. We will just take that and divide it by the number of liters, which is 0.0150 liters. And that will give us the molarity in three significant figures, 0.507 molar H2CrO4. There you go. Number 19, about 10% of the mass of Lime-A-Way toilet bowl cleaner is the main active ingredient, hydrochloric acid. Muriatic acid is sold in the hardware stores. That's that smoking stuff my husband gets for me. About 30% of its mass is hydrogen chloride or hydrochloric acid. Which one, Lime-A-Way or muriatic acid, is getting better at getting rid of the lime stain? Hydrochloric, the smoky stuff. Which one's safer? Lime-A-Way. That's why my husband doesn't want me to use the other. He tries to. 20, concentrated acetic acid is 17.4 molar. How would you make 250 mils of a 3.5 molar acetic acid solution from concentrated acetic acid?
That one could redo the
M1V1 equals M2V2. And I would suggest you do that, okay? But your choice. It's your choice. Otherwise, you can take that, go to the moles of the one that you have both things of, and then, yeah, okay, everybody's going, no, we don't want to do that. Okay, it's fine. I like easier too, that's why I showed you the other way. Number 20, concentrated acetic acid is 17.4 molar. How would you make 250 mils of 3.5 molar acetic acid solution from concentrated acetic acid? And the easiest way to do this, in my experience, is to use M1V1 equals M2V2. So we have M1V1 equals M2V2. And we have the concentration of the acetic acid is 17.4. So that is the first molarity, 17.4 molar. And we are trying to figure out how to make the others, so we are looking for the volume that we're going to add. And then how would you make, and we have the second volume, which is 250.0 mils. And we want the final molarity to be 3.5 molar. Okay, that way we've plugged everything in. And so we go ahead, we want to get this by itself. So we're going to divide both sides by that. And I'm just going to show you. And I'm going to do that over here too. So this is going to disappear from this side, isn't it? Now we are multiplying or dividing, so we do this in our calculator. 3.5 times 250 equals divided by 17.4 equals. What comes out of my calculator is 50.287 blah 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 blah. The molarity will be left with mils, but we have three significant figures here, 4 here, and 2 here. So our answer has to be in two significant figures. And so we're going to answer to this place. 2 will not roll up. So we have to do 50 in two significant figures, 50 mils. Now, I told you that in the colleges, they're allowing you to put a decimal place there to show that that is actually a significant figure. Or if you'd like, you could do it this way. And that also shows 50 with two significant figures. And that's how your book would have you to do it. But I told you a lot of the colleges are using this method, so you're welcome to use this as long as you're showing two significant figures. In 20, we got 50 mils. So you'd use 50 mils of the concentrate and dilute it with 200 more mils to get 250 mils of the 3.5 molar acetic acid. That's what that 50 represented. Number 21. A chemist makes 50 mils of a sodium chloride solution with a concentration of 2.50 molar. A student wants to use that to make a 1.75 molar solution. What volume of the 1.75 solution can he make if he uses all of the original solution? Okay, so once again, we're going to do M1 V1 equals M2 V2. And he makes a 50 mils with a concentration of 2.5. So we have the original molarity as 2.5 molar, and we have the original volume as 50.0 mils. And we want to know what volume, so we're looking for V2, we can make of a 1.75 molar solution. So we are looking for V2, so we are going to divide both sides by 175 molar. So I'm going to ditch this because they cancel, and I end up with V2 equals, so I'm going to go ahead and put in my calculator, 2.5 times 50 equals divided by 1.75. What comes out in my calculator is 71.4285, blah, blah, blah. Molar will cancel. I'll be left with mils. But we are multiplying and dividing, so we have to figure out our significant figures by which one has the least number. And all of these have 3, don't they? So this answer has to be in 3, which means we're taking it to this place. The 2 does not roll up, and therefore the answer would be 71.4 mils. And that's how much you would be able to make, is 71.4 mils. If you're having trouble with any of this, please go back and study that section of the chapter again. If you want more practice problems, go to the website and it offers you more problems that you can practice on. And I think that's always a really good idea if you're struggling with it at all. I personally just practice and practice and practice until I know how to do the problems and can do them without struggling. So I would suggest that, and then go ahead and take your test and follow your syllabus, read the first half of the next chapter, and have a very blessed week.